Hi, so the last example I want to do is a kind of random, weird distribution that I'm making up. And I'm going to make it difficult just to highlight where method of moments really shines and not being too difficult. Right, so we're going to say xi is our IID from a distribution with a PDF. I'm not going to actually write out what the PDF is, but with three unknown parameters, right? Where, let's say that the expected value of x is equal to theta 1, theta 2. Expected value of x squared is equal to theta 1 plus theta 3. And expected value of x cubed is equal to theta 2 times theta 3 plus theta 1. Sure, and now what do we do for method of moments? We set sum of xi's over n equals theta 1 times theta 2. Set sum of xi squared over n is equal to theta 1 plus theta 3. And lastly, we set sum of xi's cubed over n is equal to theta 2, theta 3 plus theta 1, right? Now, last thing I do is I'm just going to opt to write sum of xi over n as a, sum of xi squared over n as b, sum of xi cubed over n as c. I'm just doing that for my own convenience, so I don't have to write quite as much. So that leaves us with a equals theta 1, theta 2, b equals theta 1 plus theta 3, and c equals theta 2, theta 3 plus theta 1. Rearranging this first equation, we get theta 2 equals a over theta 1, which if we plug into this third equation, right, that gets us c equals a over theta 1, theta 3 plus theta 1. Guess I should emphasize now that there's no magic way to solve this specific equation. I'm just trying to solve the system of three equations with three unknowns for each unknown parameter one at a time. But how I'm going to go about doing that is finding theta 1 first. So in the second equation, we get that theta 3 is equal to b minus theta 1, right? Which, again, if you plug into this third equation, that gets us c equals a over theta 1 times b minus theta 1 plus theta 1, right? Now, rewriting that third equation, that gets us c equals a times b over theta 1 minus a, right, plus theta 1. That looks right. Or if we multiply left and right hand sides by theta 1, that gets us c theta 1 equals ab minus a theta 1 plus theta 1 squared, right? Or going to set this up and use the quadratic formula. Theta 1 squared minus a plus c theta 1 plus ab equals 0, right? So this means, using the quadratic formula, theta 1 equals a plus c plus or minus square root of a plus c quantity squared minus 4ab over 2, right? Now, if we were doing this with an actual parameter, odds are one of the two possible values, because, it could be plus or minus, wouldn't make any sense just in terms of what possible values the parameter theta 1 could have. So we write that this is theta 1 hat and then method of moments, right? And I'm just going to write this as d, again, for my own convenience. Now if you plug D into the top two equations, that will get us A equals D times theta 2, applying theta 2 hat, method of moments equal to A over D, right? Now if you plug both of those into this third equation, we get C equals A over D theta 3 plus D, or if you rewrite that, you get theta 3 hat method of moments is equal to C minus D over A divided by D. So I guess the takeaway is, even for a weird, complicated, completely arbitrary distribution that I just picked out, usually method of moments is not very computationally heavy.